Hello friends, we have learned that a circle or a straight line can be expressed in the form of an equation using coordinates. We have also learned about a pair of lines in a plane. Nidhi, what are the possibilities for a pair of lines in a plane?
Yeah, ma'am. The two lines may be parallel to each other or they may be intersecting or they may be coincident.
And what are the possibilities for a pair of circles in a plane?
Similarly, ma'am, the two circles may intersect each other or they may be touching each other or the two circles may be non-intersecting.
Suppose we have a line and a circle. Then what could be the possibilities, Nidhi?
Ma'am, the line may intersect the circle at most 2 points or one of the 2 points may come closer to the other and ultimately approaching the other. In other words, we can say that the line is touching the circle.
That's right.
Or the line and the circle may not intersect each other.
Right. Now we have learned that if a line intersects a circle at two distinct points, then this line is a secant to the circle. In case the endpoints of a line segment lie on the circle, then this is called a chord of the circle. And if a line is touching the circle at just one point, then this line is called a tangent to the circle. And a line which is drawn perpendicular to the tangent to the point of contact is called a normal to the circle. Now suppose we have a circle here. How many tangents can we draw to this circle at a point which is given on the circle?
Ma'am, it can be only one.
So we can draw only one tangent. But what about the case when the point given is outside the circle like this? Here the point given P is outside the circle.
Ma'am, then we can draw the two tangents, one this way and other this way.
So given a point P outside the circle, we can draw two tangents PA and PB.
Ma'am, in the study of straight lines, we have learned how to find whether the two lines intersect each other or not. And in case they intersect, we have also learned to find their point of intersection. Can in the line and the circle, we also find whether the line intersect the circle or not?
Oh sure, the method is very simple. We simply solve the equations simultaneously. To illustrate this, let us take an example. Find whether the line 7x minus y is equal to 25 intersects the circle x square plus y square is equal to 25 or not. If yes, find the points of intersection also.
Ma'am, here the equation of line is 7x minus y is equal to 25 and the equation of circle is x square plus y square is equal to 25. But how can we solve these equations?
Look here, we do it by elimination method. From this first equation, that is the equation of the line, we get y is equal to 7x minus 25. Now substituting this value, suppose this is equation 1 and this is equation 2, substituting this value of y in equation number 2, that is the equation of circle, we get x square plus 7x minus 25 whole square is equal to 25, which gives us x square plus, this is a minus b whole square formula. So 49 x square minus 350 x plus 625 is equal to this 25, which on solving further gives us 50 x square minus 350 x plus 600 is equal to 0. Now, we can divide throughout by 50 because 50 is common here. So, we get finally x square minus 7x plus 12 equal to 0. Now, this is a quadratic equation in x and we can solve it by factorization. So, the factors for this quadratic equation will be x minus 3 into x minus 4, these are the two linear factors, is equal to 0. So, we get the two values of x as x is equal to 3 and x is equal to 4. Now, if x is equal to 3, then we get the value of y which was 7x minus 25. So, 7 into 3 minus 25 which is equal to minus 4. So, one point of the intersection of the line and the circle is 3 minus 4. When x is equal to 4, from here again we get the value of y is 7 into 4 minus 25. Solving this we get the value of y as 3. So, another point of intersection of the circle and the line is 4, 3. So, we find that the line intersects the circle at two distinct points, 3 minus 4 and 4 minus 3. Using the distance formula, we can find out the length of this chord AB.
But ma'am, if the quadratic equation doesn't have any solution, then what can we do?
In that case, we find the discriminant. To discuss this, let us take a general case. Let the equation of the line be y is equal to mx plus c and the equation of the circle be x square plus y square is equal to r square. Now, solving these two equations simultaneously, we have x square plus we replace y square by this value mx plus c whole square is equal to r square, which gives us x square plus, now this is a plus b whole square formula. So, m square x square plus 2 times m c x plus c square, and this r square is taken to left hand side, minus r square is equal to 0. From this we get 1 plus m square x square. So, we have combined these two terms of x square plus 2 times m c x plus c square minus r square is equal to 0. Now, this is again a quadratic equation in x. So, let us find out the discriminant for this. Here d will be equal to b square minus 4ac. So, b square will be 2mc whole square minus 4, a is 1 plus m square and c is c square minus r square, which is equal to 4m square c square minus, I am opening the brackets here, 4c square plus 4r square minus 4m square c square plus 4m square r square, which further gives us the value of d as 4r square into 1 plus m square minus 4 c square. Now, this is the discriminant. In case d is greater than 0, that is, if 4r square into 1 plus m square is greater than 4c square or r square is greater than c square upon 1 plus m square, then the line will intersect the circle at two distinct points, because in that case the quadratic equation has two distinct roots. Now, if d is equal to 0, that is, if r square is equal to c square upon 1 plus m square, or r is equal to modulus of c upon under root of 1 plus m square, then in that case the line will intersect the circle at two points which are coincident, or we can say that the line intersects the circle at just one point. In other words, we say that the line is a tangent to a circle. So, we can say that r is equal to modulus of c upon under root of 1 plus m square is a condition for tangency of a line to a circle. Now, if d is less than 0, that is, if r is less than modulus of c upon under root of 1 plus m square, then in that case the line will not intersect the circle at any point, because in such a case the quadratic equation does not have any real root. Now, the condition for tangency, that is, when r is equal to modulus of c upon under root of 1 plus m square, can be used to find whether a line is a tangent to a circle or not. Nidhi, here is a problem for you. Prove that the line x plus y under root 3 is equal to 4 touches the circle x square plus y square is equal to 4. Can you do it?
Yeah, ma'am. Here we can use the condition r is equal to mod c upon under root 1 plus m square. Now, the equation of line is x plus y root 3 is equal to 4.
That is right.
And from here we can get the value of y as y is equal to minus x upon root 3 plus 4 upon root 3. So, this implies m is equal to minus 1 upon root 3 and c is equal to 4 upon root 3. Also, we have the equation of circle as x square plus y square is equal to 4, or we can write it as x square plus y square is equal to 2 square. So, from here we get the value of r is equal to 2, and if we substitute these values in the condition, we get 2 is equal to mod 4 upon under root 3 upon under root 1 plus minus 1 upon root 3 whole square. And after solving this equation, we get mod 4 upon root 3 upon under root 4 upon 3. And if we solve, we get
2 is equal to
2, which is true. So, the line is tangent to the circle. But ma'am, if the equation of circle is not in the standard form but in the journal form, then what will be the condition?
In that case also, we use the similar method, that is either solving the equation simultaneously or we find the discriminant.
Oh, so friends, we came to know that if d is equal to 0, then the line is tangent to the circle, and if d is greater than 0, then the line is a secant, and if d is less than 0, the line does not intersect the circle. Am I right, ma'am?
Yes, you are right. So, we have learned to find the point of intersection or the point of tangency of a line to a circle. We can also find the equation of a tangent to a circle at a given point. For that, we derive a result which will be quite useful. Let us take a circle with equations x square plus y square is equal to r square. Let us take a point P on this circle with coordinates x1, y1. Here is a circle. Let us take a point P with coordinates x1, y1. Let us take another point Q quite close to P with coordinates x2, y2. Then by 2-point formula, the equation of the line PQ will be y minus y1 is equal to y2 minus y1 upon x2 minus x1 multiplied by x minus x1. Also, since these 2 points lie on the circle, therefore, they must satisfy the equation of the circle. So, we have x1 square plus y1 square is equal to r square. Also, since x2, y2, that is point Q, lies on the circle, therefore, we have x2 square plus y2 square is again equal to r square. If this is equation number 1 and this is, sorry, this will be equation number 2 and this is equation number 3. Subtracting these two equations, we have x2 square minus x1 square plus y2 square minus y1 square is equal to 0, which on solving further we have y2 square minus y1 square is equal to x1 square minus x2 square. Now, using the formula a square minus b square, which is equal to a plus b into a minus b, we can open this and we have y2 minus y1 into y2 plus y1 is equal to x1 plus x2 into x1 minus x2, which further gives us y2 minus y1 upon, I am taking this to the left hand side, x1 minus x2 is equal to x1 plus x2 upon, this goes to the right hand side denominator, y2 plus y1, which further gives us, taking the negative sign common, we have y2 minus y1 upon x2 minus x1 is equal to minus of x2 plus x1 upon y2 plus y1. Now, since the tangent at P is a general case or a limiting case for the line PQ, so for we take the point Q as close as possible to the point P. In other words, we say as Q approaches P, x2 approaches x1 and y2 approaches y1. So, in the limiting case, this equation 4 tends to y2 minus y1 upon x2 minus x1 tends to become minus 2x1 upon 2y1, which is minus x1 upon y1. Now, substituting this value in equation number 1, that was the equation of the line PQ, that is y minus y1 is equal to y2 minus y1 upon x2 minus x1 into x minus x1. So, in the limiting case, this equation of line PQ becomes, we get y minus y1 is equal to minus x1 upon y1 into x minus x1, which on further solving gives us y1 minus y1 square is equal to minus x1 plus x1 square, which further gives y1 plus x1 is equal to x1 square plus y1 square, or we can write it as x1 plus y1 is equal to r square. Now, observe the change in writing the equation of a tangent at point x1 y1 from the equation of a circle x square plus y square is equal to r square.
Equation of tangent is very similar to the equation of circle. Here x square is replaced by x1 and y square is replaced by y1 and r square remains unchanged.
That is right. Now, try this problem. Find the equation of the tangent to a circle 4x square plus 4y square is equal to 5 at the point 1 half.
Ma'am, here again we will replace x square by x1
So, we get 4x x1
and y square by y1, that is 4y1 is equal to 5. And now we will substitute the value of x1 and y1, that is 4x into 1 plus 4y into 1 by 2 is equal to 5. And if we solve the equation, we get 4x plus 2y is equal to 5. So, this will be the equation of the tangent.
But we proved the result for an equation of a circle in standard form, which you did not change this equation in the standard form.
Sorry ma'am, I do it again.
There is no need, because the change will not affect the answer. So, your answer is correct. So, today we have learned about the relationship between a line and a circle and a pair of circles in a plane.
And friends, we have also learned how to find the equation of tangent to a given circle. Thank you ma'am, and thank you dear friends, but don't forget to attempt more questions related to the circles, and next time we will study about other curves in a plane. Thank you.